Welcome back. I'm going to do a brief little section now, section 2.10, direct products and sums. We'll introduce two ways to create new normed linear spaces from old ones. And even with this, there's overlap between those two different ways to be elaborated on. First definition is, as often with this stuff, it's not quite as complicated as it looks. We're going to take S to be a set, called an indexing set. And for each element, lowercase s, in set capital S, suppose X sub S is a linear space. All right, let's digest that. So how many linear spaces are there? Well, there's one for every element of set S. So the answer is cardinality of S. That's how many different linear spaces we're talking about. And cardinalities of sets can be really big. If it's a finite cardinality, then things are rather simplified, and you've dealt with this kind of thing before, even in sophomore linear algebra. But S could be more complicated than that. So that's the setting, a bunch of linear spaces, X sub S. Consider the set of all functions on set S such that f of S is an element of X sub S for all lowercase s. So we're taking an element of set S and associating it with X sub S. Take element lowercase s from set S, F takes that element into X sub S. So for each index, we call S an indexing set. So think of the little s's as indices. We're dealing with functions that map those indices into the normed linear space. They take that index and they give you a vector. So the claim that is, or the definition is, the set of all functions on S is itself a linear space, and it's called the product of the spaces, denoted with a capital Pi, product as S ranges over set capital S of the X sub S spaces. Now that is a bit of a claim, I suppose, but notice what happens. Any particular S is mapped into one of the X sub S's. The X sub S's are all linear spaces, so you can take linear combinations of these functions because component-wise, you can take linear combinations of the function values. So it makes sense for these functions to talk about linear combinations. So it's a linear space. We just need closure, I guess, under linear combinations. Nobody said anything about norms just yet. Of course, we'll have to take care of that. But here's how the product of a collection of normed linear spaces is defined. To make it more tangible, if S is simply the set consisting of 1 and 2, then we consider functions that map 1 into the space X sub 1 and map 2 into the space X sub 2. So such a function would produce an ordered pair consisting of an element of X1, comma, an element of X2. Ordered pairs because this space has 2 elements. If this space had n elements, then we get n tuples of, I guess, vectors from these n different vector spaces. In general, you want to think of this still in terms of tuples. You're getting cardinality of S tuples. If the cardinality of S is 2, you're getting pairs. If the cardinality of S is n, you're getting n tuples. And if it's more interesting than that, and the cardinality of S is infinite, you're getting some kind of tuples. Think of them as tuples, where S describes position, the little s that ranges over the elements of set S, because that certainly works here. You've got a first position and a second position in an ordered pair, but think of it that way even when S is a more complicated set. If each of the X sub S's is a normed linear space for all of the indices, lowercase s, then for Fn, the product, X sub S, define the norm of F. Okay, well, we can define whatever we want. That doesn't mean necessarily it is a norm, but more of that shortly. Define the norm of F to be the supremum of the norm of F of S as S ranges over set capital S. So what you're doing, in some sense, is in this cardinality of S tuple, you're taking, I want to say the largest component. Okay, it's not largest because set S might be infinite. If set S is finite, we can say maximum. But set S might not be finite, so we'll have to say supremum. And the components themselves are vectors. So what we've got here is definitely norms here. This is a norm from normed linear space, x sub s. For given s value, we'll have a conversation involving the norm on the set x sub s. S changes, then the norm will have to change to the norm on a different normed linear space. So how many of these spaces are there? Cardinality of S. I'm still thinking of it in terms of components. And this very much reminds me of a soup norm like we've had previously. A little bit more complicated because now we're getting for components of these vectors, not real or complex numbers, but elements of a normed linear space. Okay, so we've defined product. We're about to define direct product as something subtly different. Turns out this may well not be a norm in general on the product of all of those normed linear spaces because a soup could be infinite. Suprema can be infinite, so this soup could be infinite, and you can't have vectors have infinite norms. So there's a potential problem with that. So we can't legitimately call this a norm just yet, but we've got what I stated as a theorem, a claim that we can fix this and turn this into a norm on a subset of the product. And that subset is called the direct product. So take this norm given here, defined on the product. The claim is this is a norm, the soup norm, on not the product, but on this thing here. It's a norm on the set of all functions f in the product such that the norm of those functions is finite. So throw out the functions that have an infinite soup norm, keep those that are finite in norm. That is called the direct product of the normed linear spaces x sub s. So the direct product is initially we'll take the regular old product, so it consists of all of these functions, and then we'll throw out those functions which have infinite norm and only keep those with finite norm. That's what the direct product is. An additional claim, if each x sub s is a Banach space, then the direct product is a Banach space. So there we'd have to deal with completeness. We'd have to take a Cauchy sequence in the direct product and show that it converges to an element of the direct product. And I bet you we'd do that component-wise. We'd fix a particular component, lowercase s, and go through and see what happens in that component in terms of Cauchiness and convergence. And the fact that we're hypothesizing in this last statement that each of the x sub s's is a Banach space, and so Cauchy sequences converge in the x sub s, and we'd have a Cauchy sequence in the s component. And that Cauchy sequence would be a Cauchy sequence in x sub s, and so would be convergent because we've hypothesized here completeness of the x sub s spaces. The natural projection, pi sub s, of function f in the, we can take it to be the product. It's the direct product we'll deal with if we want to deal with any analysis stuff. So we'll throw out those vectors, but the natural projections still make sense for the regular old product of the spaces. So we're taking a function in the product or a direct product and mapping it into x sub s. As follows, take pi sub s of function f and set it equal to f of s. This can be done for any of the s's. What this would correspond to in finite dimensions, in Rn say, would be going through and taking an n tuple and picking out the sth component. Pick out one of the components, and that's how the projection stuff is done. Okay, here we're not getting scalars out, we're getting vectors out. So a touch more complicated here, but that's basically the idea. The subspace of the product, which consists of all functions that take a value of 0 except for finitely many values of s, is the direct sum of the x of s's, as s ranges over that set capital S. So what that means is not only will this direct sum involve vectors which are finite, it's going to involve vectors that only have finitely many non-zero components. Let's call them components. They're vectors in a linear space, so it makes sense to talk about components. There's a bunch of components. There's cardinality of S components, but anyhow. So what we get is bunches and bunches and bunches and bunches of zeros potentially, and just finitely many non-zero components in such a vector. If that's the case, it's called a direct sum of those vectors. So for direct product, we've thrown out all vectors that are infinite with respect to this sup norm. And what we've done in the direct sum is throw out all vectors that have infinitely many non-zero components. An observation, just jump down here real quick. If set S is finite, then there's no distinction between the direct product and the direct sum. There's nothing to throw away. If S is finite, then all the vectors just have, say, n components, if n is the cardinality of S. So there'll be vectors that are finite in length in the sup norm, and they'll have all but finitely many non-zero components because they only got finitely many components. So there's some overlap there. I said initially we got two different ways to deal with these products, direct products and direct sums, but there's some overlap in those. These ideas might look vaguely familiar to you from a modern Algebra 1 class. We deal with direct products and direct sums of groups as well. And in that class, talk about regular direct products, kind of the way we did here. A weak direct product, also called a direct sum, where you do this all but finitely many or zero idea, but in a group setting. 0 would represent the identity in the group in that case. All but finitely many are the identity from the respective groups. And you talk about canonical projections or natural projection. So you'd have a projection concept in the group setting, just like we have here. I like that because this stuff is kind of geometric, and it's very rare in an algebra class that I can try to talk about something that's somewhat geometric. And that takes care of direct products and sums. Next section is also quite brief. In the next section, we'll look at, we'll revisit the concept of a basis of a normed linear space and have a couple of takes on that, foreshadowing some things we'll do when we get into the Hilbert spaces. We'll see you in section 211, Schroeder bases, shortly. Have a nice day.